As we mentioned earlier, all of the amino acids that we've discussed are chiral and exist as a pair of enantiomers, or potentially exist as enantiomers, except glycine, because glycine has an R chain that is just a hydrogen, and therefore the alpha carbon in that molecule is not a chiral center. So it doesn't have an enantiomer because it will be superimposable on its mirror image. L-amino acids are the primary form of amino acids found in nature, and all of the amino acids, all of the main 20 amino acids, are in fact L-amino acids. So D and L nomenclature is based on D and L glyceraldehyde, which is a small sugar, and we'll talk about that in just a minute. The R and S nomenclature that you used in organic chemistry is actually superior, because amino acids like isoleucine and threonine can have two chiral centers, and they can be named therefore unambiguously according to the version that you have if you use the R and S nomenclature. Now, you're only going to have one type of these in nature, so it really isn't that important if you're dealing with purely biological systems, but if you stray from that and you're doing some research, you may need to use the R and S nomenclature for amino acids. And we're going to look at that in just a little bit, and I'm sure you remember that from organic chemistry. In biochemistry, we use Fischer projections primarily for drawing different, for demonstrating different 3D conformations of molecules, especially when it deals with sugars. And so you can see here that we have how to draw a Fischer projection. So a Fischer projection is basically a cross, okay, that demonstrates 3D configuration where everything on the vertical is going away from you, okay, and everything on the horizontal is coming out at you. Okay, so if we draw wedges and dashes, we would draw wedges on the horizontal, and I haven't drawn this very well, dashes on the vertical, okay, like you see here up here at the top. So that Fischer projection is a way of representing that 3D shape of the molecule with just lines, which is much easier if you're doing something large like a sugar. Sugars have a lot of chiral centers, and here's an example of glucose. Okay, you can see all of the chiral centers in glucose, and this one is demonstrated as a Fischer projection. So all of these carbons that are in pink are actually chiral, and so this would be a Fischer projection where all of the verticals are going away from you, and all of the horizontals are coming out at you. Now, most molecules are not going to really exist in that type of conformation. It's just a shorthand way of denoting stereochemistry so that we're not drawing all of these wedges and dashes. And so we draw a Fischer projection. Most sugars have an aldehyde group at the top and a CH2OH at the bottom, and then they're going to have some OHs across the middle. Okay, and if that OH on the middle, let me just draw the other one here, draw the enantiomer here of this molecule. Okay, so if the OH at the bottom is on the left side, then that is L, the L sugar. And that's actually not what it means. It doesn't mean left, but that's a good way to remember it. If the bottom OH attached to that bottom chiral carbon is on the left, then it's an L sugar. And if that bottom OH attached to the bottom chiral carbon is on the right, then it's a D sugar. Okay, so in this case we have D glucose, which is the normal form for glucose. Actually, what that stands for is dextrorotatory and levorotatory because of glyceraldehyde, which actually rotates plain polarized light. Levorotatory for L and dextro for D. Okay, and so Why do L amino acids predominate in biological systems? Well, we need to have one type of amino acid because if we had different ones, our proteins would have really strange structures. It keeps our protein structure regular and in in other words, we'll see these alpha helices and beta sheets that we form. We wouldn't form those regular structures if we had random configurations on our amino acids. And so there was a meteorite that entered Earth's atmosphere a few years ago, and it actually was found in Australia, and it was found to have a lot of biological compounds in it. So if you're interested, you can look up more information about this meteorite, this Murchison meteorite, and it was found to have an L enantiomeric excess of 2 to 15%. So it did actually have some D amino acids, so it had these amino acids here. It also had a lot of other molecules, a lot of hydrocarbons and life molecules that originate from life forms. So it was a very unique discovery, but it did land in a barn, so there was a lot of speculation about this meteorite, and you can look it up if you're interested in more information about it. But it didn't have all L amino acids. Alright, and so we can see here that we have L-glyceraldehyde. So let's go ahead and see how we would use that, how we would convert that to the R and S system. So here we have a Fischer projection, which is usually written as CHO for the aldehyde group, CH2OH at the bottom, and then we have our H's and OH's across the middle coming out at us. Okay. So if we want to convert this to R and S system, we're going to rotate that that COH group down. I'm sorry, went the wrong way with it. We're going to rotate that CHO group, the aldehyde group, to the left. Okay, and so that's going to bring our OH up to the top. Now, if you're confused about this, it would be good to make a model with a tetrahedral carbon. So get your models back out and put like a red, blue, white, green ball. I'm sure you remember doing that from organic chemistry on your black carbon ball and practice rotating this. So like the red might be the CHO, green might be CH2OH, or yellow might be this and white might be this, or however you want to do it. And so when you rotate it, then the CHO group, aldehyde group will go over here, CH2OH will go over here, because we're going to rotate this hydrogen toward the back, and our OH group is going to come up toward the top. So you're going to point the lower priority group away from you, okay? So what you're going to do is prioritize these groups according to atomic number. Remember that from organic chemistry, and so from atomic number, oxygen is number 8. Oxygen is number 8, carbon is number 6, nitrogen is number 7, okay, fluorine is number 9, I don't think we're going to be dealing with that one, sulfur is number 16, so these are some common ones that we'll be using. Hydrogen's number 1, that's generally going to be your lower priority group here. And so let's look and see what we have. Remember, we move away until we find the first point of difference. So in this case, what's attached to our chiral carbon? We've got oxygen, carbon, carbon. So oxygen is going to be priority number 1. Then we've got a tiebreaker between the carbon and carbon. Now both of these carbons are connected to an oxygen, but remember an aldehyde group looks like this. In fact, I'm going to draw this. An aldehyde group looks like this. Let's get it up here. COH. Okay, that's better. So this carbon has oxygen, oxygen, hydrogen, and this carbon has oxygen, hydrogen, hydrogen. Okay, so if you don't remember how to do this, it would be good to go back and review that. I'll try to remember to put a link down below to a video where I go over that. And so this one is going to be priority 2, and this is going to be priority 3, because our hydrogen is number 4. So going 1 to 2 to 3, this is S-glyceraldehyde. Okay, so S is going to be L. I mean, L is going to be S, I'm sorry. Now, D-glyceraldehyde is just the opposite, so we have the opposite. We have our CHO over here, and so we're going to go clockwise, so that's going to be R, so for rectus, and so we'll go 1 to 2 to 3, the progression of rotation, and this is R glyceraldehyde. Okay, so for alanine, we have our center carbon here. Okay, so we're going to rotate this. So this is an amino acid. We have L-alanine here. So we're going to rotate this so that our COOH, or they've actually pulled the hydrogen off here, and they have it on here. I don't think it really matters. But anyway, we'll just be consistent. So if you flip this around, the methyl group is going to come over here. The COOH is going to go over here, and the amine group will go up. The hydrogen will be pointing toward the back, so get a model kit and practice with that, or if you don't have a model kit, use some gumdrops or something. And so we have nitrogen is number 7, carbon is number 6, and carbon is number 6. So we've got carbon versus nitrogen. This is going to be priority number 1. Then we have to break the tie here. This carbon has oxygen, oxygen, hydrogen. This carbon has hydrogen, hydrogen, hydrogen. So this is going to be number 2. This is going to be number 3. So progression of rotation is 1 to 2 to 3. So this is S-alanine. Okay. Now you're given these priorities, functional groups down here, but you really don't need that. You just need to learn how to do this for yourself. And it's much easier when you just do it that way rather than memorizing all this stuff. So just get a periodic table and a handheld model and do these for yourself, and I'll put a link down below. Thanks for watching. I'll see you in the next video.